Hello and welcome to NPTEL MOOC on fiber optic communication systems and techniques. In this module we continue our discussion of light transmission through the fibers using the ray optics approach. And I hope you remember this picture that I have drawn here, where we had light incident from N0, which is coming from outside, making an angle of theta 0 with respect to the axis of the fiber, which is the normal to this optical fiber and air interface. Once it hits this core or the optical fiber end face of the optical fiber, then it gets refracted into the cladding, and once the angle of incidence theta 1 at the core cladding interface is greater than or equal to critical angle, equal to is not really the correct way to look at it, because then the light would be propagating along the boundary. So, you want the light to make an angle theta 1 which is actually greater than the critical angle, so that this light ray can be reflected off. But even if you were to just assume at the boundary level kind of a thing that the minimum value of theta 1 required for total internal reflection would be the critical angle, then it is easily calculated. So, the sin theta 1 c, which is the critical angle, sine of the critical angle for the core and cladding interface, is of course given by N2 by N1. Please remember that N1 is greater than N2 because core always has a higher refractive index than the cladding for these type of fibers. Okay. So, you have sin theta 1 c equals N2 by N1, but if I go back to this part of the figure and then apply Snell's law at the end face of the fiber, so I will have N0 sin theta 0 being equal to N1 sin phi 1. But from this geometry, from the red line, the blue line and this black line, that simple triangle that you have, we can see that phi 1 is basically 90 minus theta 1, where 90 is basically 90 degrees actually. So, 90 degrees minus theta 1 or pi by 2 minus theta 1 in case you are expressing them in terms of radians. Okay. So, this is pi by 2 minus theta 1, let us say. Okay. Now, I can substitute for phi 1 into this expression and rewrite sin phi 1 as sine of pi by 2 minus theta 1, and then using the sin A minus B formula, which is sin A cos B minus cos A sin B. So, this is essentially cos of theta 1. So, this becomes N1 cos theta 1. And as I have told you, if I were to look at this ray of light which is incident or which is there at the core cladding interface just at the critical angle, okay, when theta 1 becomes equal to theta 1 c, sin theta 1 c is N2 by N1, and then I will make theta 1 as theta 1 c, okay, for whatever the value of theta 0 that this happens. And clearly if sin theta 1 c is N2 by N1, cos theta 1 c is square root of 1 minus N2 square by N1 square. So, I can put that into this expression and write N0 sin theta 0 equals N1 square root of 1 minus N2 square by N1 square. So, I can rewrite this one. So, I will have N1 square minus N2 square under root, okay, and then N1 comes out and cancels off with this N1. Usually the outside medium we take to be air. So, we take it to be air, so that N0 actually is equal to 1, because the outside medium, as I told you, is air. So, what I have is a relationship which governs the angle of incidence to the optical fiber end face or the input of the optical fiber. The sine of that angle of incidence must be equal to N1 square minus N2 square at the critical value, because if I now consider an angle theta 0 which is greater than this maximum angle, see the blue line, or let us actually rewrite the lines. Okay. So, let us say I have a red line which is the maximum angle theta 0 that I can make, okay, which I will call as theta 0 max, such that once it goes into the fiber, it just barely makes an angle of critical angle here, okay, and then light would continue to propagate just on the interface between core and the cladding. Okay. So, this is the extreme condition. If I were to send in light which is marked by this particular ray, okay, so this is marked by this ray because it is falling outside this angle would go into the fiber at an angle which is actually less than critical angle and therefore won't really propagate inside the fiber, but kind of major part of it goes onto the cladding side. Only some part gets reflected, but again most of the part goes in the cladding, some part gets reflected. Because of multiple reflections, it keeps losing energy, because every time it hits the core cladding interface it kind of loses energy, and therefore this black ray of light would not really propagate for a very long distance. So, we have a maximum value for theta 0, okay, and this maximum value of theta 0, okay, is called as the acceptance angle of the fiber. For single mode fiber, this is given by square root of n1 square minus n2 square. Okay. The sign of this one is given, therefore, this acceptance angle is inverse of sine square root of n1 square minus n2 square. Now, this is very interesting, right, and this kind of gives us the first parameter to look for when I am going to use optical fibers for different applications. Having this theta 0 max, that is acceptance angle much larger, allows me to actually use a light source, either a laser or something, which would typically be sending off light in this manner. So, if I have this angle of incidence, which is, or if I have this acceptance angle to be quite wide, okay, and of course acceptance angle is actually an acceptance cone, in the sense that you have a same theta 0 max onto the other side as well. Light is in the form of this cone, or this acceptance angle actually makes a cone kind of a thing. So, having a larger value means that I am able to tap in or couple more light from the light source, okay, because if I have a fiber whose acceptance angle is very small. So, let us say this is the fiber, I am running out of colors to write here. So, I am hoping that this will be visible to you. So, if the acceptance angle of a hypothetical fiber is just this orange cone, right, then you can very clearly see that we will not be able to get as much light as we would have obtained with a fiber which has a larger acceptance angle. This works in the other way around as well. So, I go to the receiver side, okay. So, I am now at the receiver side, light is coming out of the optical fiber in this manner. If the fiber has a larger acceptance angle, then the fiber will come out with a larger cone, and then I can either put a lens and then converge it and then put this onto a detector, okay. But if light comes out over a very small region or a very small cone, then I will not be able to couple much of the light into the detector. So, most of the light is actually sitting inside here if the acceptance angle is small. So, acceptance angle on one hand tells you how much light can be coupled into the fiber, on the other hand acceptance angle also tells you how much light can be delivered to the detector, okay. And if you want to have a high efficiency coupling system, you want to be able to capture much of the light that comes from the light source and be also able to deliver much of that light into the detector, okay. So, right away there is a trade off. In a standard single mode optical fiber, this acceptance angle is actually quite small. So, coupling light is not very efficient. So, one has to devise methods to efficiently couple light into these standard single mode fibers, but the trade off here is that those single mode fibers have only one mode and therefore eliminate dispersion based on intermodal dispersion, which is present in the multimode fibers. We are going to discuss all these dispersion concepts later on. So, do not worry about it right now, but you just understand that having multiple modes for long distance communication is not always good, because it can destroy information in the form of intermodal dispersion, okay. It can distort information, okay. So, for that purpose, so if you want to carry light over very long distances across thousands of kilometers with very minimal distortion, then you want single mode fibers which come with a smaller acceptance angle. However, if I am working with a biomedical probe, I am going to make a probe to detect something on the skin or just deliver light on the skin, then obviously I need a fiber with a larger core area or a fiber with a larger acceptance angle and delivery angle. Why? Because I have to gather light that is incident or that is reflected from the tissue, okay, and as much light has to be gathered, because that reflected light itself is usually quite weak, okay. So, you want to be able to collect as much light and also to deliver as much light, okay. So, if you were to go for that application, having fibers with a larger larger acceptance angle is very important, and in those fibers it is usually the multimode fibers which are used, because these multimode fibers have a larger acceptance angle. Okay. So, anyway, so you have this acceptance angle thing that we talked about. The sign of this angle is what is normally called as the numerical aperture. Okay. So, you want a fiber to have a very good numerical aperture, and again in a single mode fiber the numerical aperture is usually half of that of the multimode fibers. Okay. So, this is a fairly standard analysis that I have done. So, I have in fact assumed a step index fiber, because I have not really looked at the graded index fiber and defined the numerical aperture accordingly for that one, but this should give you the basic idea of what this numerical aperture is all about. Okay. So, you want a fiber with a larger numerical aperture, but you then have to trade off that with the other things. We have also discussed the V parameter, right. So, we know that V parameter is given by 2 pi by lambda times A square root of n1 square minus n2 square, and we have said that if this is less than 2.405 you have a single mode fiber, if it is greater than 2.405 then you have a multimode fiber. Okay. So, how exactly this works out I am going to tell you that, but in case you know the V number of a given fiber, then approximately the number of modes that the fiber does support is given by V square by 2. So, when you have a V value of say about 10, then the number of modes that you can support is about 50, which is very very large. Okay. So, this is what you have about some of the important parameters of the optical fiber. So, when you go to market and buy an optical fiber, you are looking for a numerical aperture, you are looking for its acceptance angle, and of course, the V number of that one, which is determined by the geometry of the optical fiber itself, what is its core radius and things like that. For standard single mode fiber, the core radius A goes anywhere between 3.9 to 4.1 micrometer. The cladding radius B is usually standardized to about 125 micrometer. Okay. For a multimode fiber, and the refractive index difference N1 minus N2 is about 0.01 or maybe sometimes less than that percentage. Okay. So, which means that N1 and N2 are very very close to each other, almost like they are equal, but there is a very small difference between the two. Okay. For a multimode fiber on the other hand, the core radius is actually quite large, it is anywhere between 50 to 62.5 micrometer, and the cladding is still standardized at 125 micrometer radius, and then you have all those core coating and other things. N1 minus N2 can still be kept the same. Remember, I have reduced, I have kept N1 minus N2 same, but to increase the V number I have increased the core radius. So, I have traded off, or I have actually kept this constant, this is anyway constant, but then increased A to support the multimode fibers. Okay. But you can also find out N1 minus N2 to be slightly larger in a multimode fiber, so that you can support even more modes if you wish. But the problem with these multimode fibers is that these multimode fibers are going to distort signal because of an important distortion mechanism called intermodal dispersion. Okay. What is this intermodal dispersion? Suppose consider light incident at an angle which is say exactly equal to theta 1 c. This is core, this is cladding, I am only showing you the core cladding interface. Okay. So, light is incident at an angle theta 1 c, and clearly for theta 1 c is the angle made with respect to this normal, of course. So, because of angle being at theta 1 c, the ray of light actually starts to propagate just along the core cladding surface. Okay. So, if there is an information sitting here, maybe in the form of a small pulse, then this pulse will be propagated. This pulse is of course with respect to time. So, this is a light ray incident. Okay. And this light ray is actually a pulse of light that is incident at this angle theta 1 c, and this pulse of light will travel through this fiber. Okay. Because this is a multimode fiber, when you incident light, you normally cannot just incident light at an angle only at theta 1 c or at a specific angle. Each of these angles which are allowed, okay, will correspond to different modes. So, this will be the fundamental mode, this will be the next mode, this will be the next mode, and so on and so forth, okay, or rather the fundamental mode comes from the other side, but anyway, do not worry about that. So, you have this next ray of light which is also carrying the same impulse or which is carrying a pulse, okay, incident, and now this fellow starts to propagate, okay, and it would arrive at the output of the fiber. So, if this is my output of the fiber that I am considering, it would arrive at this point with a slightly different velocity, okay, or let us not consider this as the output. What I am going to consider is to actually let this ray of light go all the way back. So, I am going to do something like this. So, this is not very nice in the sense that I am considering the angles not correctly, but please forgive me, this is just to for illustration purposes. The blue light is also propagating, carrying an impulse, okay, it is also propagating and carrying an impulse, but at a different velocity than the other rays of light, right. So, what you actually have seen is that if I were to consider this multimode fibers, okay, in these multimode fibers one starts to, when one couples light into these different modes, identical information, identical pulse to these different modes, each of those rays of light which carry these pulses arrive or travel through a fiber, okay, with different velocities, okay, and because they are traveling with different velocities, at the output what you would see is one pulse coming here, another pulse coming after some time, another pulse coming after some time, and when you place a detector at the output of the fiber, what you get is essentially one big pulse or one broadened pulse, which would then limit how quickly you can transmit these pulses again. If you imagine each pulse carrying an information at a certain rate, so that is one pulse every TB seconds, let us say, having a bit rate of 1 by TB or bit rate of RB, okay, then you have a constraint on how quickly you can transmit these pulses, because you have to give a certain time, or you have to understand that when you transmit a pulse over a duration TB, then the pulse duration can actually increase because of intermodal dispersion, and that can play or that can limit the rate at which you are transmitting information. Okay. If you want to estimate what is roughly the limit of this bit rate because of intermodal dispersion, you can consider two rays, okay, one ray which is incident at the critical angle, okay, and then the other ray which is kind of incident straight up through the fiber. Okay. So, if I consider a fiber of length L, the ray of light which is travelling along the axis, let us say, will be reaching the receiver in a time frame of, or the minimum time of, L by V, okay, where V is basically C by, or V1, let us say V1, because the velocity of light inside the core is basically C by N1. Okay. But what about the ray of light that is incident at an angle? So, if I have a ray of light incident at an angle, then it will cover the same length L, okay, in a different time. So, for example, if my angle of incidence is theta 1, this angle is also clearly theta 1. The overall distance here is L, but this distance L, so this is the half distance. So, this is theta 1 again, this is theta 1 again, and the length over which it has actually propagated, right, is given by, in terms of this hypotenuse, this would be given by, so if I call this as say 0.1, 0.2, the length of 0.1 and 2, which I will call as L12, is this one. So, in terms of L12, this distance is basically L12 sine of theta 1, because sine theta 1 is opposite by hypotenuse, right. So, I mean going by the basic trigonometry of this one. So, this length is L12 sine theta 2, and let us say I call this part as 3 or this point as 3, then this would be L23 same angle sine theta 1, because it has totally internally reflected. So, theta 1 is of course greater than theta 1 c, please understand that one or keep that in mind. If I consider the distance 1 to 3 and call that entire distance as L, then that distance L will be the sum of these two distances, and the velocity with which, or the time delay that is now taken by this ray of light, which is actually making an angle of theta 1, is given by L12 sine theta 1 plus L23 sine theta. So, this one is sine theta. So, this is L12 sine theta 1, L23 sine theta 2. So, for the ray that is given by this blue line. If I assume that the distance between 1 to 3 is L and there is a symmetry out there, so that this length which is going from 1 to say some intermediate point I, these are not very nicely labeled, but please excuse that. So, the length from 1 to I, if I call that as L by 2, and then the length from I to 3 is another L by 2, then the actual length that the ray propagates to get from 1 to 3 is this length L12 plus L23, right. And what is this length L12 in terms of L by 2 and sin theta? I know that sin theta 1 is given by the intermediate length 1 to I from this triangle. Okay, so, from this triangle that I have, it is given by L by 2 divided by this length L12. So, L12 is L by 2 sin theta 1. Okay. Clearly, L12 is L by 2 sin theta 1. Similarly, L23 will also be L by 2 sin theta 1. The total length of propagation will be for an angle theta 1, I mean as a function of angle theta 1 is given by L by sin theta 1. Okay. And therefore, the time taken for the ray of light which is actually propagating along this blue line, making an angle of theta 1 with respect to the normal core cladding interface, is given by L by sin theta 1, and it actually does this in a time span of, or with a velocity v1. Therefore, the time taken is given by L by sin theta 1 times v1. Okay. And I know that v1 is given by c by n1, which is the phase velocity of the ray of light inside the core. Therefore, the time taken for theta 1 or an ray of light which makes an angle of theta 1 is given by n1 L by c sin theta 1. Clearly, the T min condition that we derived, that is the minimum time taken by the ray of light which is propagating horizontally, okay, because horizontal means theta 1 equals pi by 2 is valid over here. So, when theta 1 is equal to pi by 2, you have n1 L by c, which is exactly what the expression for T min that we actually found out, right. So, if you combine these two equations, you will see that what we have obtained is the same equation. So, you have n1 L by c when theta 1 equals pi by 2 and the ray of light is travelling in this manner. Okay. The maximum time is taken by that ray which actually travels just at the angle of critical angle. So, when your angle is just at the critical angle, then it would take maximum time duration for it to propagate, and that can be obtained by letting theta 1 equals theta 1 c and recognizing that sin theta 1 c is basically given by n2 by n1. Okay. So, the maximum time is now taken by the ray given by n1 L divided by c. Sin theta 1 c is basically n2 by n1. So, therefore, n1 goes on to the top, I think. So, you will have n1 square L by c n2. This is the maximum time duration. So, arriving at 0 or at whatever the time which is taken, minimum time of arrival as measured from 0 axis, and then you have another one which is arriving, okay, with a max angle of, or with a max time of T max, and there will be all these intermediate pulses. So, corresponding to different angles of theta 1 between, this is for theta 1 equals pi by 2 and this is for theta 1 equals theta 1 c. For all angles between them, they would all be arriving at different times which are between T min and T max. So, your overall pulse would actually be at least of this broadened value. So, you have seen that. So, you have just seen that the pulse essentially gets broadened, and if I had only a single mode of propagation, then I could just transmit right after this arrives at the receiver T min, then I could transmit another pulse. Okay, so, maybe another pulse follows here. So, this pulse would come arrive at the same time T min. So, it would be possible for me to send multiple pulses, pulses at a much faster rate, because the pulses are not getting broadened. Okay, we are ignoring other types here, but the pulses are not getting broadened, but because of this broadening nature, I have to wait for quite a bit of a time. At least I have to wait for a time duration of T max minus T min. Okay, is the amount by which it is broadening, right. So, I have to wait until this time delta t before another pulse can be launched. So, because this T max minus T min, which is essentially determining the amount of pulse broadening, is coming because of multiple modes, same information carried by multiple modes of the fiber. This type of a dispersion, which was very widespread in the 1970s fibers, is called as intermodal dispersion. Intermodal means dispersion or the difference in the velocity giving rise to pulse broadening because of multiple modes in a multi-mode fiber. So, this is the pulse broadening that you are going to obtain, and you can actually substitute for the expressions of T max and T min and find out the expression for delta T, which turns out to be N1 L by C N1 by N2 minus 1. So, I am going to rewrite this one as N1 L by C N1 minus N2 divided by N2. Okay. So, this is the expression for the amount of pulse broadening delta T, and this pulse broadening eventually has to be in such a way that if the pulse is broadened by less than, say, amount of TB, which is the pulse or the bit slot that I am sending out. So, if this delta T is less than or equal to TB, then this is one criteria, of course. So, if I let that the pulse broadening be less than the time slot or equal to 1 time slot, then I will be able to communicate at this particular rate. Okay. So, if I impose this condition, then I will actually get, and since I know that TB is basically 1 by RB, you can rewrite these conditions in terms of RBL being less than or equal to Cn2 divided by N1 square delta, where delta is usually given by N1 minus N2 by N1. Okay. So, you can go back to even this expression, multiply by N1 on both sides, and therefore, this becomes N1 square, and what you have is N1 square L delta by Cn2. Okay. So, this would be the expression for delta T, and because I need to restrict my pulse broadening to less than the time period TB, that will itself impose the amount it will impose a limit on the amount of or the rate at which I can transmit pulses and hence information. Okay. So, this product RB times L, where RB is the bit rate and L is the length of the fiber or the length of propagation, is very important. So, this is called as distance bandwidth limitation or bit rate length product. Okay. So, for the fibers, this bit rate length product is reasonably large, but for a copper this bit rate length will be very small, and of course, that explains one of the reasons why we switched over from copper to optical fibers. Okay. We will do a more rigorous analysis of dispersion in the coming modules, but for now it is important to understand whatever that has been done is only based on the ray theory approach. We have not really looked at how electric fields are distributed inside the fiber and how they propagate, what essentially happens at the core cladding interface. To do all that, we need to look at electromagnetic wave nature of light and use Maxwell's equations to study light propagation inside the fiber. Thank you very much.